Hello, this is Jack Jackson back again in our series of lectures on discrete probability. In fact, we're in the middle of a small series of lectures on multi-stage probability. And in this video, we're going to talk about probability trees, introducing those. And we're going to do this with an experiment of having two children. Okay. So here's the experiment. We're going to have two children. For any particular child, what is the probability that it is a female child? So the probability of a girl. So let X be the random variable, which is the total number of female children. Now we're saying we definitely will have two children in this particular situation. So what are the possible values of X? And then the question is each value of X equally likely, or is one possibility more likely than the others? What do you think the probabilities are for each value of X? Now, while we can't feasibly conduct this actual experiment, it's going to take quite a while for everybody to have two children, not to mention a lot of other problems with that. But we could simulate this. Think of how you could simulate this in a reasonable amount of time without actually, of course, having children. But how could you do this? And go ahead and simulate it, simulating 40 pairs of children. And then see if that simulation gives you results that are reasonably the same as what you thought for your probabilities. So see if the empirical probabilities from the simulation agree with what you thought the theoretical probabilities are. And it's going to take a minute for you to work all that out. So go ahead and do that. Come back when you think you've got all that done. Press pause now. Well, the probability that it's a female is 1/2. Well, actually, the probability of a girl is actually very slightly higher than the probability of a boy. But this difference, at least in the United States, but this difference is so extremely small, we're going to ignore it throughout this course and assume that the probability is exactly 1/2 for a female. Of course, that means probability of male is exactly 1/2 as well. And X is the total number of female children when you're having two children, so X is either 0, 1, or 2. If you're only having 3 children, you can't have only 2 children. You can't have 3 females. If you can't have 1.5 or something. So it has to be 0, 1, or 2. Is each value of X equally likely, or is one possibility more likely than the others? It turns out that X equals 1, in other words, 1 girl, and of course that'd be 1 boy, turns out to be more likely than having 0 girls, and it's also more likely than having 2 girls. We'll see exactly what it is here in a little bit. Okay, and what do you think the probabilities are? Did you come up 1/3, 1/3, 1/3, thinking these are equally likely, or did you put a higher probability for 1 than for 0 or 2? Or did you do it some other way? We're going to work out what the actual probabilities here are in the following slides. Now remember, we can't feasibly do this, but some kind of experiment we could do that would simulate this would be just doing something that we could repeat that has a probability 1/2. So for example, you can simulate with flipping a coin. So like we could say, flip a coin twice, record the number. If it's a heads, it's a girl. Flip it twice. How many heads you get? That's one trial, and record it either 0, 1, or 2. Put a tally mark. Flip it another 2 times. Or you could roll a pair of dice. Say an even number would be a girl, and you'd count how many even numbers you get on each roll. That would be another way to do it. And so hopefully if you've done this for 40 children, then you can come up. Now, your results will definitely vary from person to person. But you should see more 1s than 0s and 2s, and about the same 0s and 2s. Okay, so one way we can keep track of this is what's called a probability tree. And we're going to try to make a probability tree here. And then after we get our probability tree, we're going to use that to make a table of all the possible values of X and their probabilities. In other words, a PDF table, probability density function table. And then make a graph, that'd be a little bar graph, of these probabilities, which is our PDF graph. Okay, so let's do that. Since this is the first time I've introduced the idea of a tree, I'll work you through the details. So we start out here with our tree at what we call our root vertex. So it doesn't really mean anything except that that's where we're starting. And then this next column of vertices, these little dots, are our possibilities. A male for the first child, female first child. And the edges going from there are the probabilities. So this is the probability we get a male the first time, which is 1/2, and the probability we get a female the first time, which is also 1/2. On the first set of edges here, these are basic probabilities. Now, what do you know about these probabilities? Well, they've got to add up to be 1. So whether there's 2 branches, only 2 possibilities here, or 3 or 4 or 5, or 100, doesn't matter. All these probabilities must add up to 1. They don't always have to be equally the same probability, but in the case of having children, they would be. So in this kind of a graph or tree, these little dots here are called vertices, or vertex for singular, vertices for plural, and these little line segments connecting the vertices are called edges. And so we label the edge with the probability, and then the events are on the vertices. Okay, so these are all the non-overlapping possibilities are from this starting point are listed, and so that means all these probabilities must add up to 1 because these are non-overlapping and they take care of all the possibilities. Okay, so then what we do next is we say, okay, this column was for the first child, now we do for the column for the second. Now, if you had a male for the first child, you could still have a male for the second, or you could have a female for the second. If you have a female for the first child, you could have a male for the second or a female for the second. So each one of these has 2 branches. Now, what goes on these edges here are conditional probabilities. Now, the first one's just a straight probability. But the second branch, the second set of probabilities, or if we had a third or fourth or fifth or sixth branch, those would also be conditional probabilities. So this is the probability, what goes on this branch is the probability we get a male child the second, given that we had the male the first. Well, now these probabilities are what we call independent, because the probability that we have a male child the second has nothing to do whether we had a male or female the first time, so it's still probability 1/2. And similarly, the probability of a female the second time, given we had a male the first time, is also 1/2. So in fact, all the edges in this tree are going to be labeled 1/2. Down here, this is the probability that a male the second time given a female the first time, which is probability 1/2, and this is probability of female second time given female first time, also 1/2. Notice that the probabilities coming out of this vertex add up to 1, and the probabilities coming out of this vertex add up to 1. Now remember, these are conditional probabilities. These are just basic probabilities. Now, think about this. What can we do with, say, these 2 probabilities, half here and half here? Probability of female 1 is 1/2. Probability of female 2 given female 1 is also 1/2. Do you remember something we could do? Now notice you can't really add these probabilities up because they don't really they're not non-overlapping, right? Certainly having a female the second time when we know that the female the first time has something to do with the female the first time, right? So here, but the probabilities here add up to 1. These probabilities add up to 1. These add up. But we can't add down this way. But there is another operation we could do. You know what it is? Well, it's multiplication. Remember that if we take a probability of B times the probability of A given B, that gives us the probability of the intersection. And similarly over here. So we can multiply probabilities along a path. So for example, let's take this path. We take the probability of a male the first time is 1/2, and the probability of a male second time given a male first time is also 1/2. Well, probability of male given the first time times probability of male given male second time given male first time, that is exactly the probability that it's both male first time and second time, which is this path. So this path says that both events happen. male first time and male second time. That's an intersection. So I could have used intersection instead of and here. And that turns out to be a half times half, or 1/4. And so similarly, you can do that for every one. So probability of male first time times probability of female second given male first is this path times this path, those probabilities. Again, half times a half, so it's a fourth. And then multiply these two here to get a probability of fourth here and probability of fourth here. So it turns out that each one of these paths is equally likely in this case. There are 4 paths. They each have a probability of 1/4. So the probability of male both times is 1/4. Probability of female both times is 1/4. Probability of male first, then female is 1/4. Probability of female first, then male is 1/4. Now notice these 4 probabilities at the end are intersection probabilities. They're the intersection of all the events along that path that get you there, like these two here. And you get them by multiplying the probabilities, because this second one is a conditional probability. And these events are non-overlapping. Okay, so they add up. Notice that they all 4 add up to 1. So all these probabilities at the end of the tree have to add up to 1. Also notice that these two are the only ones coming out of male first time, so they should add up to the probability that you get a male first time. So 1/4 plus 1/4 is 1/2. So these are the only two going back to this vertex. They're all of them that go back to that vertex and nothing else. So they add up to the probability of getting to that vertex. Same way down here, these two add up to the 1/2 from here. Now in this case, each one of these is equally likely, and that's because all the probabilities were 1/2. Now, we're going to look at examples later on where we're looking at things where the probability might not be a half. For having children, it is a half, male, half female, but it doesn't have to be that way for some other situations. Plus, everything doesn't always have to have 2 branches, and it doesn't have to be too deep. So we'll look at all kinds of variations of this as we go. But there's an example of a completed probability tree. Now let's go from the probability tree to the PDF table and graph. Well, our X is our number of female children, so that could be either 0, 1, or 2. Well, this one right here is 0 female. Male and male, that's 0 female. So that happens with probability 1/4 or 25%. The only one to get 2 is this one right here, female, female, and that's also probability 1/4. But notice there are 2 of them that have X equals 1. Male, then female, female, then male. So that's both X equals 1. You add those probabilities, 1/4 plus 1/4 is 1/2, and so we get that. So did you come up with that earlier? Half the time you should get 1 female, and hence 1 male. And then only 1/4 of the time would you get 0 females and 1/4 2 females. And of course, if you graph that, that makes the bar in the middle twice as tall as the other 2 bars. So this is the graph of the PDF and the table for the PDF. And there's the probability tree. Okay? Let's see if you followed me. And let's do another example. So this is going to be a bit harder and longer. Let's take the same thing we just did, but let's extend the tree out and say we're going to have 4 children. So let X be the random variable that counts the total number of female children, and make a probability tree and label all the probabilities. Label probability on every edge, and also figure the probabilities at the end for the intersection of all along the path. And even though we're going to have 4 things, it turns out you can multiply all the probabilities along the path to get the probability of the intersection at the end of the path. So once you have the tree made out, then make a table and graph of the PDF. This may take a minute, but go ahead and do this and come back when you're finished. Press pause now. Well, if you look at this, the solution turns out to start out just exactly like the other tree. I didn't label each one of these, but every probability here is a half, because each of these events is independent. So male the first time, a half. Female first time, a half. This one, that should say 1/2, not 12. 1/2 is the probability of a male second time given a male first time, and that probability is male second time given male first time. This one up here is probability of a male the third time given a male first time and a male second time. So it's the probability of this one conditional on everything earlier happening. And this last 1/2 is the probability of a male the fourth time given a male the first, second, and third times. But of course these are all independent, so they're all 1/2. So it turns out in this case there's 16 outcomes, all equally likely. So each one has probability 1/16. And again, we can get that by just multiplying the probabilities like along the bottom here. 1/2 times 1/2 times 1/2 times 1/2 is 1/16. And in fact, that's true all the way. But now let's go back and see how that lines up with X. Now, X is a number of female children. If you're having 4 children, you could have either 0, 1, 2, 3, or 4 females. If you look, the only way that you could get 0 children that are female is to have male, 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 male. It's only this top branch, top path, all the way across is 1/16. Similarly, the only way you can have 4 females is to go female, 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 female. It's the only path is this bottom one, this red one of 1/16. Now it turns out all of the ones I've got as green 1/16 are the ones that have X as 1. So 1 female. It could be male, 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 then female, female in the last time. Male, female for 4th child. It could be female for the 3rd, the other's male. That would be male, male, female, male. Okay, and it looks like this is out of order. Looks like that one should be the green one there. And this one should be the brown one, but I still got the right amount altogether. Okay, and then I have, let's see, another way we could do the female in the 2nd child. So that would be male, female, male, male. That's another green one there. And then down here we should have female first time, and then male, male, male. All of those are 1. So there's 1, 2, actually this one, 3, 4 of those that had 1 female. So that's 1/16 plus 1/16 plus 1/16 plus 1/16. So 4/16, which is 1/4. So 25% of the time that will happen. Similarly, 25% of the time there'll be 1 male, which is 3 females. And you can see those like female, 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 male. That's this purple one. Female, female, male, female. That's another purple one. Female, male, female, female. That's 3 females. That's this purple one. And hopefully, if we got this right, this purple one here will be as well. Male, female, female, female. Yeah, that's 3 females. And we've got that. So there are 4 of those purple ones that add up. 1/16 plus 1/16 plus 1/16 plus 1/16 equals 4/16 or 1/4. And all the ones that are left, that are the tan ones, once we switch the 2 colors up here, that are the ones that get 2. So that could be male, male, female, female. That one should be tan. That one should be green. What do we got? Male, female, male, female. That's 2 females. That's that one. And so forth. And if you count those, they're 1, actually this one, 1, not that one, 2, 3, 4, 5, 6 of those. So that's 6/16, which reduces to 3/8. And of course, if you add all those fractions up, you do get 1. Here is the percentages over here. Actually, they terminate, so those are all exact percentages. So here's what we get. It's symmetric about the middle here of 2. 2 is still the most common. 3/8 of the time that will happen. And then 1/4 of the time you'll either get 1 or 3 females if you have 4 children. 1/16 of the time it'll be either 4 females or 0 females. Okay? Let me... Okay, let's look at another example. Okay, this one, let's just use the properties we know about probability trees to fill out some other missing information. So here we have an incomplete tree. Okay, so we have a tree, we start at the root vertex. The first event could either be A, B, or C, and regardless of which one of those happens, it's possible to get either D or E for the second stage. And I have some probabilities labeled. What's this one? What's the 0.2? Well, that's just the probability that A happened. What's the 0.3? It's the probability that C happens. What about the 0.5? Well, that's the probability that D happens given A happened. How about the 0.6 then? This edge. So that's the probability of E given B. And this is the probability of D given C is 0.2. So use what you know about probability trees to completely finish out the edges on the probabilities here. Come back when you're done. Press pause now. Well, the fact that we're going to use is the fact that these probabilities all have to add up to 1. So 0.2 plus 0.3 is 0.5. 1 minus 0.5 leaves 0.5 for the probability of B, because exactly one of A, B, or C have to happen. Similarly, once A happens, exactly one of D or E happens. Since D is 0.5, 1 minus 0.5 is 0.5 for the probability of E given A. Given that B happens, either D or E has to happen. So if this one's 0.6, we get 1 minus 0.6 equals 0.4 for the probability of D given B. And if the probability of D given C is 0.2, these two probabilities have to add up to 1, so 1 minus 0.2 is 0.8. So these three add up to 1, these two add up to 1, these two add up to 1, these two add up to 1. So all the probabilities coming out of a single vertex have to add up to 1. Now, we also have probabilities that are supposed to go here at the end of the tree. Remember, these three probabilities, the 0.2, 0.5, and 0.3, are just straight probabilities. Probability of A, probability of B, probability of C. These probabilities on the second set of edges, are actually called conditional probabilities, and the ones at the end are probabilities of the past, which are intersection probabilities and probabilities. And so the probability of A and D, or probability of A intersect D, goes out here. Figure out those 6 probabilities and come back when you're done. Well, hopefully you remember that all you have to do to find the probability at the end is multiply the probabilities along the path. So we're using, for example, probability of A intersect D is probability of A times probability of D given A. That comes from our definition of conditional probability we did just a little bit earlier. So probability of A is 0.2, probability of D given A is 0.5. That multiplies together to be 0.1. In other words, you just multiply these two probabilities to get the one at the end. Similarly, 0.2 times that 0.5 is 0.1. 0.05 times 0.4 is 0.2. 0.5 times 0.6 is 0.3. 0.3 times 0.2 is 0.06. And 0.3 times 0.8 is 0.24. Now, what you should know is if you add up all these green probabilities, what do you get? Well, you get 1, right? Okay. Furthermore, notice that if you add up these two, they add up to this probability right here, since they're the only way to get out of A. So 0.1 plus 0.1 is the 0.2. The 0.2 plus the 0.3 is the 0.5, and the 0.06 plus the 0.24 is the 0.3. Can we go backwards now? What if we only have the probabilities at the end? Can we go back and fill out some of the other information? Is that enough to fill out the whole tree? Use that fact that I just showed you to fill out the probability of A, the probability of B, and the probability of C. Go ahead and do that and come back when you're ready. Press pause. Well, remember, these two add up. They're the only ones that come out of A, so they must add up to the probability of A. 0.2 plus 0.1 is 0.3. 0.3 plus 0.15 is 0.45, and 0.05 plus 0.2 is 0.25. Now, can we figure out the missing ones on this one, which are conditional probabilities? See if you can figure that out and come back. Well, remember, we multiply these two, the missing one right here, times this one to get that. Well, if we know the answer to a multiplication problem in one of these, we can divide to get the missing one. So if we take the 0.2, the intersection, divided by the probability of the one we know, 0.3, that gives us, well, 2/3 in fraction form, and that's the conditional probability. That's the definition of conditional probability. Similarly, the 0.1 divided by 0.3 is 1/3 for this one here. 0.3 divided by 0.5 is 2/3. 0.15 divided by 0.45 is 1/3. 0.05 divided by 0.25 is 1/5, and 0.2 divided by 0.25 is 4/5. And a check is that these two have to add up to 1, and these two add up to 1, and these two add up to 1. And of course, all three of these have to add up to 1. And all the green ones have to add up to 1. So now we know some of the basic structures in probability trees. We can use this to help us make probability trees and use that to compute some different probabilities. Only given sort of partial information, we can now get a complete tree if we're given the right information and can work that out. So we're going to put this to work in some real-world examples in the subsequent videos.